The German U-boat fleet had turned the Atlantic into a graveyard, but technology was about to change everything. And at the center of this transformation was one man, one brilliant insight, and one deceptively simple antenna design that would make the undetectable detectable, and then, remarkably, turn the tables once more. This is the story of how science changed the course of the war beneath the waves. In the early months of 1943, the Allied forces faced a crisis that threatened to decide the outcome of the entire war. The German submarine fleet, the Kriegsmarine's U-boat arm, was sinking merchant vessels faster than they could be replaced. The statistics were staggering. In the first 20 days of March alone, over 90 ships went down. That represented more than 500,000 tons of desperately needed supplies, food, ammunition, and equipment sent to the bottom of the Atlantic. The men in the operations rooms in London could see the pattern clearly. Red pins marked each loss on the great map of the Atlantic. The pins clustered together, forming what the officers grimly called the Black Pit, a vast area of the mid-Atlantic where aircraft couldn't reach, where convoys traveled alone and vulnerable. Here, the wolf packs hunted freely. Groups of U-boats, sometimes 20 or 30 strong, would gather around a convoy like predators, circling wounded prey. But the men tracking these patterns noticed something else, something that gave them hope. When aircraft appeared, the submarines vanished. When ships equipped with the newer detection equipment came close, the U-boats dove deep and disappeared. The technology was working when it could reach them. The problem was range, and specifically, the problem was radar. Radar had been one of the war's great secrets. The British had developed it before the conflict began, using it to detect incoming German bombers during the desperate days of the Battle of Britain. The principle was elegant in its simplicity. Send out a pulse of radio waves. If those waves hit something, an airplane, a ship, a submarine, they bounce back. Measure the time it takes for the echo to return, and you can calculate the distance to the target. Plot multiple returns, and you can track its movement. By 1943, radar had evolved considerably from those early warning systems. Scientists had learned to use different wavelengths for different purposes. Longer waves could reach farther but gave less precise information. Shorter waves, what they called centimetric radar because the wavelengths were measured in centimeters, could paint a much clearer picture of what they were seeing. An aircraft equipped with centimetric radar could spot a submarine's conning tower from miles away, even in complete darkness or through thick fog. There was just one problem. The submarines were learning to hide. In the research laboratories scattered across Britain and North America, scientists worked around the clock on the detection problem. They were a mixture of university professors, industrial researchers, and brilliant young minds pulled from civilian life and thrust into uniform. Many had never worked on military problems before. They brought with them ideas from physics, mathematics, electrical engineering, and a willingness to try approaches that the established military contractors would have dismissed as impractical. Among these researchers was a team working on what seemed like a peripheral problem. They weren't trying to detect submarines. Instead, they were trying to help submarines avoid detection. This might sound contradictory, but by 1943, the Allies were playing a complex game. They needed to understand German technology to counter it. They needed to know what their own submarines faced when they operated in enemy waters, and critically, they needed to develop better equipment for their own vessels. The team was led by a physicist who had spent the pre-war years studying the behavior of radio waves. His name was rarely mentioned in the official histories, as so much of his work remained classified for decades. We'll call him by what his colleagues called him, simply the Professor, as that captured both their respect and the academic world he'd left behind. The Professor understood something fundamental about radar that many military men didn't fully grasp. Radar wasn't just about transmitting a signal and receiving an echo. It was about the complex interaction between electromagnetic waves and physical objects. The size of the object mattered. Its shape mattered. The material it was made from mattered. And critically, any metal structure sticking up from that object mattered most of all. A submarine running on the surface presented multiple radar targets. The hull itself would return some signal, but the real problem spots were the vertical structures, the conning tower, the periscopes, the snorkel mast that allowed diesel engines to run while submerged, and most problematic of all, the antennas. Early submarines had carried relatively simple radio equipment, a wire antenna strung between masts, or a rod antenna that could be raised and lowered. These worked well enough for their purpose, allowing the boat to receive orders from command and report its position and findings. But they had a fatal flaw in the age of radar. They were perfect radar reflectors. A vertical metal rod, particularly one tuned to radio frequencies, acted like a mirror for radar waves. An antenna designed to receive signals at certain wavelengths would naturally reflect those same wavelengths very effectively. This made the submarine visible to radar at much greater ranges than the hull alone would. A U-boat running on the surface to recharge its batteries, its antenna deployed to maintain communication, might as well have been carrying a beacon saying, "Here I am. Come sink me." The German submariners learned this harsh lesson through bitter experience. Aircraft would appear seemingly out of nowhere, having spotted them from beyond visual range. Attacks would come in darkness or fog when the U-boat crew thought they were safe. The pattern became clear. Stay on the surface with your antenna up, and you'd be found. The solution seemed obvious. Limit radio communications. Run dark when possible. But this created its own problems. Submarines that maintained radio silence couldn't coordinate their attacks. They couldn't warn each other of threats. They couldn't receive updates on convoy positions or changes in orders. The U-boat fleet's greatest strength had been its ability to mass its forces against convoys, to strike with overwhelming numbers. Without reliable communications, that advantage evaporated. The professor saw this as a problem that could be approached scientifically. If you couldn't eliminate the antenna, could you make it less visible to radar? Could you design something that would still work as an antenna, receiving and transmitting radio signals, but that wouldn't light up every radar screen in the Atlantic? The answer, he believed, lay in understanding exactly how radar waves interacted with different shapes and structures. His team began a series of experiments that would have looked strange to any outsider. They built scale models of submarine antennas and tested them in special chambers lined with radio-absorbing material. They mounted the models on turntables and fired radar pulses at them from different angles, carefully measuring the strength of the returns. What they discovered was both simple and profound. The amount of radar energy reflected didn't just depend on the size of the antenna. It depended on its shape, its orientation, and most critically, on its cross-sectional profile to the incoming radar waves. A thin rod seen end-on reflected very little energy. Seen from the side, it was much more visible. A complex antenna array with multiple elements could return strong signals from some angles and weak ones from others. The strength of the return varied by factors of 10 or even 100 depending on the viewing angle. This led to an insight. What if you could design an antenna that presented a minimal profile to radar regardless of the angle? What if, instead of trying to make it invisible, which was impossible, you made it consistently insignificant? An antenna that would blend into the background noise, that would return such a weak signal that it couldn't be distinguished from wave clutter and sea spray. The conventional antenna designs of the time were all variations on the same theme. Vertical rods, either single elements or arrays of elements. They stuck up because that's what made them work well as antennas. Height mattered for radio communications. The higher the antenna, the farther it could reach over the horizon. but that height made them radar beacons. The professor's team began exploring alternatives. What if the antenna wasn't vertical at all? What if it was horizontal, lying flat, or nearly flat? A horizontal wire or rod would present a much smaller target to radar, especially to airborne radar looking down. Yes, it wouldn't work quite as well as a vertical antenna for long-range communications. But if it was good enough for the ranges submarines actually needed, then the trade-off might be worth it. They built prototypes. Long, thin wire antennas that could be strung along the length of the conning tower, or even embedded into its structure. Flat spiral antennas that could be mounted flush against horizontal surfaces. Each design was tested for its radio performance and for its radar signature. The results were promising, but not yet good enough. The horizontal antennas worked, but they had their own problems. They were more susceptible to damage from waves breaking over the submarine. They picked up more noise from the motion of the vessel through the water, and for transmitting, they required more power to achieve the same range as a vertical antenna. Then the professor had his crucial insight, the one that would make everything work. The problem wasn't really the antenna at all. It was the way people thought about antennas. Everyone assumed you needed one design that did everything, receive and transmit, all frequencies, all conditions. But what if you didn't? What if you could use different antennas for different purposes, each optimized for its specific role? A submarine didn't need long-range transmission capability most of the time. It needed to listen, to receive orders and intelligence. Only occasionally did it need to transmit, to report enemy positions or request instructions. And those transmissions could be brief, compressed bursts that revealed the submarine's position only momentarily. With this insight, the team designed a system rather than just an antenna. For receiving, they would use a low-profile antenna that was nearly invisible to radar. It wouldn't be the most sensitive receiver in the world, but it would be good enough for signals from powerful shore-based transmitters. For transmitting, they would use a different antenna, one that could be quickly raised, used, and then retracted. The submarine would expose itself to detection only during those brief transmission periods, and it could take precautions during those times, such as transmitting only when aircraft weren't nearby. But the real elegance was in the receiving antenna itself. The professor didn't just make it horizontal. He made it a different shape entirely. Instead of a simple wire or rod, his team developed what they called a slot antenna. Imagine cutting a thin groove into a metal surface. That slot, if properly sized and shaped, could act as an antenna. It could be built directly into the conning tower structure, invisible to the eye, presenting almost no profile to radar. The slot antenna had been known in theory, but nobody had tried to use it for this application. It required careful engineering. The slot had to be exactly the right length for the radio frequencies in use. It needed to be fed with radio energy in a specific way. The metal around it had to be configured properly. But once those details were worked out, the result was remarkable. In tests, a submarine conning tower fitted with the new slot antenna system was virtually invisible to radar compared to one with conventional antennas. The radar cross-section, the measure of how much signal it reflected, dropped by over 90%. An aircraft that could have detected the old antenna configuration from 20 miles away would have to get within 2 or 3 miles to spot the new design. And at 2 or 3 miles, the submarine's lookouts would likely spot the aircraft first, giving them time to dive to safety. The first operational tests were conducted in the cold waters off Scotland. A British submarine, equipped with the new system, played the role of a U-boat. RAF Coastal Command aircraft, equipped with the latest radar, flew search patterns trying to find it. The submarine ran on the surface, maintaining communications with shore stations, doing everything a German U-boat might do. The aircraft struggled. Time and again, the submarine remained undetected until it was close enough that the crew could hear the engines. The pilots were frustrated. They knew roughly where the submarine was supposed to be. They had good radar equipment. The weather was clear, but their screens remained stubbornly empty until they were almost on top of the target. When the submarine was finally brought back to port, the pilots came down to see what they'd been trying to find. They walked around the vessel looking for the antennas they'd been unable to detect. Several of them walked right past the slot antenna without noticing it. It was just a thin line in the metal of the conning tower, something that might have been a weld seam or a construction detail. Even when it was pointed out to them, they found it hard to believe that this subtle feature was what had made their job so difficult. The success of the trials led to immediate questions. Could this technology be used to protect Allied submarines operating in hostile waters? Absolutely. Should it be shared with the Americans and other Allied nations? Yes, through the usual secret channels. But a darker question also emerged. If the British had figured this out, might the Germans do the same? Intelligence reports from captured U-boat crew members suggested that German scientists were also working on the radar detection problem. They had developed their own solution, a device called METOX, which could detect the radar pulses from Allied aircraft, giving the submarine warning to dive before the plane got close enough to attack. This was a different approach, defensive rather than stealthy, but it showed that German engineers understood the threat and were developing countermeasures. The professor's team was asked to think like the enemy. If German scientists were working on this problem, what would they develop? Would they come up with something similar to the slot antenna? Or would they take a different approach? The team wargamed various scenarios. The conclusion was sobering. German engineering was excellent. Given time and motivation, they could certainly develop low-profile antenna designs. The question was whether they would prioritize it, given all the other demands on their research establishment. As 1943 progressed, the Battle of the Atlantic began to turn. The tide shifted not because of any single technology, but because of an accumulation of advantages: more escort ships, better training, improved tactics, breaking of German codes which allowed convoys to route around wolf packs, and yes, better radar and detection equipment. Aircraft with centimetric radar forced submarines to remain submerged more often, reducing their effectiveness. When they did surface, they could be found and attacked before they located their prey. The U-boat fleet suffered terrible losses. In May 1943 alone, 41 U-boats were destroyed. Admiral Dönitz, commanding the submarine fleet, was forced to withdraw his boats from the North Atlantic temporarily, conceding defeat in that critical battleground. The crews who survived spoke of the constant fear of aircraft appearing without warning, of radar that seemed to see through darkness, and weather. But in the secret world of naval intelligence, analysts noticed something else. Some U-boats seemed to avoid detection more successfully than others. Some boats survived encounter after encounter, slipping away when they should have been caught. Were their commanders just luckier, more skilled, or did they have something else, some technological edge that wasn't in the intelligence reports? The answer came in fragments. A captured German sailor who mentioned new antenna equipment. A U-boat damaged and forced to surface, photographed by reconnaissance aircraft before it went down, showing unusual structures on its conning tower. Intercepted radio messages discussing technical modifications to submarine communications gear. Individually, none of these fragments meant much. Together, they suggested that German engineers had indeed found their own solution to the radar detection problem. The professor's team was proven right. German scientists had developed their own low-profile antenna designs. They weren't identical to the British slot antenna. German engineering philosophy was different, favoring robust mechanical solutions over elegant electrical ones. But the principle was similar. They had created antennas that presented a reduced radar signature while maintaining adequate communications capability. This created a new challenge. If both sides had stealth antenna technology, the advantage would go to whoever had the better detection systems overall. It became a competition in sensitivity. British radar operators were trained to watch for the faintest blips on their screens, the subtle returns that might indicate a submarine with reduced radar signature. They developed techniques to distinguish between real targets and false echoes from waves and weather. The Germans, meanwhile, improved their METOX warning receivers and developed new versions with greater sensitivity and better ability to identify the type of radar being used. A U-boat commander who knew what kind of radar was tracking him could make better decisions about when to dive and when he might risk remaining on the surface. This technological competition continued throughout the war. Each side would gain a temporary advantage, then the other would respond. Aircraft got better radar. Submarines got better warning receivers. Antenna designs evolved to become even stealthier. Detection algorithms became more sophisticated. It was an invisible war fought by scientists and engineers, running parallel to the visible war fought by sailors and airmen. One of the remarkable aspects of this story is how little the frontline forces knew about the technological battle being fought on their behalf. A U-boat captain didn't understand the physics behind his new antenna design. He just knew that he seemed to be detected less often when he used it properly. An RAF pilot didn't know about slot antennas or radar cross-sections. He just knew that some targets were harder to find than others, and he adjusted his search patterns accordingly. The war in the Atlantic was ultimately won not by submarines or by the ships hunting them, but by the slow accumulation of industrial and technological advantage. By 1944, the Allies were building ships faster than U-boats could sink them. Allied aircraft covered more of the ocean. Code breaking gave advance warning of submarine positions. The U-boat fleet was still dangerous, but it was no longer the existential threat it had been in 1942 and early 1943. But in that crucial period when the outcome was uncertain, when the Battle of the Atlantic could have gone either way, technology like the low-profile antenna made a real difference. It didn't win the battle alone. No single innovation ever does. But it helped shift the balance, made the hunter's job a little harder, gave submarine crews a slightly better chance of survival. In a conflict decided by narrow margins, those small advantages mattered enormously. The professor and his team never received public recognition during the war. Security classification prevented any mention of their work. The official histories, published years later, glossed over the technical details, referring vaguely to improvements in antenna design, without explaining what those improvements were or how significant they had been. For decades, the story remained buried in classified documents known only to a handful of specialists. When the details finally emerged, long after the war, they revealed a pattern that would be repeated throughout the Cold War and beyond. The pattern of a technological competition where each side's advances drove the other to innovate faster, where today's secret advantage became tomorrow's standard equipment and next year's obsolete technology, where brilliant minds worked in isolation, often unaware that their counterparts on the other side were solving the same problems in different ways. The slot antenna and its variants found new life in the decades after World War II. The principles the professor had discovered about minimizing radar signatures through careful design became foundational to the field that would later be called stealth technology. Modern military aircraft, ships, and submarines all incorporate features designed to reduce their radar visibility. Some of those features can be traced directly back to that wartime work on submarine antennas. The engineers who worked on the F-117 stealth fighter in the 1970s and 80s studied the World War II research. The designers of the B-2 bomber drew on the same fundamental principles. Every modern naval vessel incorporates lessons learned from the professor's experiments with radar cross-sections and antenna placement. The field had grown vastly more sophisticated, with computer modeling and exotic materials replacing wartime trial and error, but the basic insights remained valid. There's a deeper lesson in this story, Beyond the technical details and the historical specifics, it's about how innovation happens under pressure, how necessity truly does mother invention. The professor and his team weren't trying to make a revolutionary breakthrough. They were trying to solve a practical problem. Submarines needed to communicate, but their antennas made them vulnerable. Could they design something better? The revolutionary part came from being willing to question assumptions, to ask whether an antenna really had to look and work the way everyone thought it did. This is how technology advances, not usually through dramatic eureka moments, but through countless small insights and improvements. The slot antenna wasn't a magical solution. It had limitations and drawbacks, but it was better than what came before, and that was enough. The next team would make it a little better still, and the team after that would find new applications for the underlying principles. The men who served in submarines during World War II never knew how much science was working to protect them or to hunt them. They focused on the immediate reality of depth charges and torpedoes, of cramped living conditions, and the crushing pressure of the deep ocean. The technology was just part of their equipment, no more mysterious or interesting than the engines or the diving planes. But for every sailor at sea, there were researchers on shore working through problems that the sailors would never see, calculating antenna patterns on blackboards, testing prototypes in laboratory chambers, analyzing combat reports to see what worked and what didn't. The visible war at sea was supported by an invisible war of ideas and innovation. The Battle of the Atlantic was ultimately a battle of resources and production. The side that could build more ships, train more crews, and replace losses faster would eventually win. But technology served as a multiplier, making each ship more effective, each aircraft more lethal, each submarine more survivable. The margin between victory and defeat was narrow enough that these technological factors truly mattered. Consider the mathematics of convoy warfare. A convoy of 40 merchant ships escorted by 6 destroyers would be attacked by a wolf pack of 8 U-boats. If the U-boats could sink 5 ships per attack and the destroyers could sink 1 U-boat, then the submarines would win the trade. They could keep attacking convoys until the merchant fleet was destroyed, accepting losses but inflicting greater ones. But if technology shifted those numbers even slightly, the equation changed. If better radar and detection equipment meant the destroyers could sink 2 U-boats per engagement instead of 1, the exchange became unsustainable for the Germans. If low-profile antennas allowed submarines to avoid detection long enough to break off attacks and escape, they could preserve their forces for future operations. Every change in capability rippled through the strategic calculations. The professor understood this. His work wasn't about achieving perfection. It was about shifting probabilities. If his antenna design made submarines 10% harder to detect, that translated into some percentage fewer submarines lost, which meant more attacks on convoys, which influenced the overall campaign. You couldn't point to any specific ship saved or lost because of the antenna design, but averaged over hundreds of engagements, the effect was real and measurable. This is the nature of technological warfare, a truth that would become even more evident in later conflicts. Individual heroism and tactical brilliance still mattered, but increasingly, outcomes were determined by which side had better equipment, better information, better systems. The side that could see farther, communicate faster, and respond more effectively would prevail, even if its soldiers weren't more courageous or its commanders weren't more clever. The German U-boat service fought with tremendous courage and skill. Their commanders were experienced and aggressive. Their crews were highly trained. But by 1944, they were facing an opponent that could see them coming, track their movements, and mass superior forces against them. Technology had tilted the playing field. Individual excellence couldn't overcome systematic disadvantage. When the war ended, both sides had extensive files on submarine technology and radar. The Americans, British, and Soviets all captured German equipment and documents. They studied what the Germans had developed, looking for ideas that could be adapted or improved. The Germans had indeed created their own versions of low-profile antennas, different in detail but similar in concept to Allied designs. Neither side had held a monopoly on innovation. This led to an interesting historical question. If both sides developed similar solutions independently, did it matter who did it first? In a purely technological sense, perhaps not. But in terms of the war's outcome, timing was everything. The Allies developed and deployed their improved antenna systems in 1943, just as the Battle of the Atlantic reached its crisis point. The Germans were slower to field their equivalent technology, hampered by production bottlenecks and competing priorities. That time difference, measured in months, coincided with the period when the tide turned decisively against the U-boats. We can't say that the low-profile antenna won the Battle of the Atlantic. Too many factors contributed to that outcome, but we can say that it helped, that it was part of the complex web of technological, tactical, and strategic advantages that eventually decided the contest. And we can recognize the brilliance of the insight that led to it, the willingness to question assumptions and approach an old problem from a new direction. The professor returned to academic life after the war, though he continued to consult on defense matters. He published papers on antenna theory and electromagnetic propagation, never directly mentioning his wartime work, but incorporating lessons learned from it. Students who took his courses learned about slot antennas and radar cross-section reduction, though they might not realize they were learning declassified military secrets. His colleagues who had worked on the project scattered to universities and research laboratories across the Allied nations. They carried with them knowledge and experience that would shape the next generation of radar and antenna engineering. Some went on to work on early warning systems for nuclear bombers. Others helped develop satellite communications. A few contributed to the space program, applying principles of electromagnetic design to spacecraft antennas and radar systems. The technologies they pioneered during the war became the foundation for post-war innovations. Commercial aviation depended on radar for air traffic control. Weather forecasting improved dramatically with radar for tracking storms. Eventually, radar became so commonplace that most people forgot it had once been a closely guarded military secret, a technology that helped determine the outcome of the Second World War. But in the quiet corners of naval research establishments, in the classified laboratories where today's military technology is developed, engineers still study those wartime innovations. They still cite the professor's papers, now decades old, because the physics he described hasn't changed. Radio waves still behave the way he calculated they would. Antenna design still follows the principles he laid out. The applications have evolved, but the fundamentals remain. Modern submarines bear little resemblance to their World War II ancestors. They're nuclear-powered, able to stay submerged for months. They're larger, faster, and far more capable. Their sensors are sophisticated beyond anything imagined in 1943. But they still face the same basic challenge, how to communicate while remaining hidden. And they still use antenna designs that can be traced back to that simple insight about reducing radar cross-sections. The antennas themselves are more advanced now. They can be extended and retracted automatically. They can handle multiple frequencies simultaneously. They incorporate materials that absorb radar energy rather than reflecting it. Some submarines use masts that rise above the surface for only seconds, just long enough to transmit or receive a burst of data, then disappear again beneath the waves. But the underlying principle, minimize your visibility while maintaining your capability, comes directly from the professor's wartime research. In recent years, with many World War II records declassified, historians have been able to piece together a more complete picture of the technological war beneath the waves. They've found documents showing the professor's original calculations, his sketches of antenna designs, his test reports. They've interviewed the few surviving veterans who remembered the new equipment being installed on their submarines and the orders to use it carefully to maintain the security advantage. What emerges from these records is a portrait of scientific warfare at its most intense. Both sides threw their best minds at the problem. Both achieved remarkable results with limited resources. Both kept their innovations secret for as long as possible, knowing that knowledge of a capability was almost as valuable as the capability itself. And both discovered that technological advantage was always temporary, that the opponent would eventually catch up, forcing another round of innovation. This pattern of thrust and parry, innovation, and counter-innovation defined much of the technological war. It wasn't limited to antennas and radar. Code makers competed with code breakers. Aircraft designers tried to build faster planes, while radar engineers tried to detect them at greater ranges. Torpedo designers improved their weapons, while ship designers developed better countermeasures. Every advance prompted a response. Every solution created a new problem to solve. The men who fought this technological war understood that they were engaged in a race with no finish line. There was no perfect antenna, no unbreakable code, no undetectable submarine. There was only the constant struggle to stay ahead, to be a little better than the opposition, to force them to respond to your innovations while you were already working on the next generation of improvements. Looking back from our vantage point 8 decades later, we can see how significant these wartime innovations were. They didn't just help win a war. They laid the groundwork for the technologies we rely on today. Radar is everywhere now, in our weather stations and air traffic control, in our police speed traps and our collision avoidance systems. The principles of stealth technology, of managing electromagnetic signatures, influence everything from military aircraft to cell phone antenna design. The story of the submarine antenna isn't just a piece of World War II history. It's a case study in how innovation happens, how pressure and necessity drive creative solutions, how questioning assumptions can lead to breakthroughs. The professor didn't have exotic materials or unlimited funding. He had a problem, some basic scientific principles, and the freedom to think creatively about solutions. His simple antenna design, simple in concept, though complex in execution, showed that elegant solutions don't require massive resources or revolutionary new physics. Sometimes they just require seeing an old problem from a new angle, being willing to challenge conventional wisdom, and having the determination to work through the technical details that turn a good idea into working hardware. As the last veterans of the submarine war pass away, taking their first-hand memories with them, we're left with documents and artifacts, the physical remnants of that desperate struggle. Among those artifacts are the actual submarine antennas from the war, preserved in museums and naval archives. They look unremarkable now, just pieces of metal and wire, shaped in ways that seem arbitrary without understanding the physics behind them. But those shapes were carefully calculated, each dimension chosen for a specific purpose. They represent countless hours of calculation and testing, the accumulated wisdom of scientists who understood that lives depended on their work being correct. They're physical embodiments of human ingenuity applied to the deadly serious business of warfare. The Battle of the Atlantic was decided by many factors. Industrial production, yes. Code-breaking, absolutely. Improved tactics, and better training, certainly. But also by innovations like the low-profile antenna, technological advantages that shifted the odds just enough to make the difference between victory and defeat. The sailors who survived to return home never knew about the scientists working to protect them. The scientists never knew which specific sailors benefited from their inventions. But together, separated by barriers of classification and military necessity, they formed a partnership that helped determine the war's outcome. In the end, the story of the submarine antenna is really a story about human problem-solving under pressure. It's about what happens when intelligent, dedicated people are given a crucial problem and the freedom to pursue unconventional solutions. It's a reminder that in warfare, as in peace, innovation often comes from unexpected directions, from people willing to question whether things really have to be done the way they've always been done. The professor's insight that you could make an antenna less visible to radar by changing its shape and configuration seems obvious in hindsight. But that's the nature of truly elegant solutions. They seem inevitable once you've seen them, even though nobody thought of them before. They open new possibilities, change what people believe is achievable, and set the stage for the next generation of innovations. Today, when military planners talk about stealth technology, when engineers design low observable aircraft and ships, when researchers work on the next generation of detection and counter-detection systems, they're continuing a tradition that traces back to that wartime work on submarine antennas. The tools are more sophisticated now, the understanding deeper, but the fundamental challenge remains the same. How do you accomplish your mission while remaining hidden from those who would stop you? The answer the professor found that sometimes the best way forward is to question your assumptions and think differently about the problem remains as valid today as it was in 1943. His simple antenna design, simple in concept but profound in implications, changed the course of the war beneath the waves. It saved lives that would otherwise have been lost. It helped secure the supply lines that kept Britain fighting and supplied the forces that eventually liberated Europe. Not bad for what started as a question about how electromagnetic waves interact with pieces of metal. Not bad at all for a scientist who simply refused to accept that things had to be done the way they'd always been done, who believed that with enough thought and careful experiment, even the most intractable problems could yield to solution. His legacy lives on in every stealth aircraft that flies, in every submarine that patrols beneath the seas, in every system that manages its electromagnetic signature to avoid detection. The ocean stretches endlessly, dark and impenetrable, just as it did in 1943. Beneath those waves, submarines still patrol, carrying missions that remain classified. Above them, detection systems still search, using principles that trace back to those desperate wartime years. The technology has advanced beyond anything the professor could have imagined, but the fundamental questions remain the same. How do you see what doesn't want to be seen? How do you hide when someone is looking for you? Those questions, asked and answered in the crucible of the Second World War, continue to drive innovation today. And somewhere in that history, in the story of one scientist's elegant solution to a deadly problem, we find both a reminder of what was at stake during those dark years and an inspiration for how human creativity and determination can overcome even the most daunting challenges. The simple antenna that made submarines undetectable to radar wasn't magic. It was science, carefully applied, brilliantly conceived, and effectively executed. It was one small piece of a vast technological competition, but it was a piece that mattered. And in a war decided by narrow margins, where every advantage counted, that was more than enough. The ocean stretched endlessly before them, dark and impenetrable. Beneath those waves, in the cramped metal confines of a submarine, men held their breath. Above them, invisible waves of electromagnetic energy pulsed through the air, searching, probing, hunting. It was 1943, and the Battle of the Atlantic had reached its most desperate hour. For every convoy that crossed the ocean, for every ship that carried supplies to Britain, there was a hunter lurking below,